Okay, cool. So I'm going to be talking about ways that you can structure your code for when you're dealing with data set. And hopefully we'll be covering different types of data sets and different packages that you might be using to deal with those data sets. So as you can see, a couple of the ones that I'm going to suggest that you use are Pandera and Pydantic, but we'll talk about that later. The first thing I'd like to talk about is actually dictionaries. Specifically, some of the downsides to using dictionaries. Now, I'm not going to say never use dictionaries. They're a tool that you should use in some cases, but when we're specifically dealing with structured data sets that we're trying to explore and work with, especially on a regular basis as a part of a pipeline or something more long-term, you might want to be thinking about using something else for three main reasons, I think. And those are lack of structure, mental overload, and issues with extensibility. I'll talk through those. What do I mean by lack of structure? Well, dictionary keys can be anything. Not quite. They have to be hashable, but nearly everything can be a dictionary key, which can cause some problems because usually they're strings, but for a lot of data sets, they're not necessarily like that when we first receive them. Let's see how that could go wrong. Let's take a simple function which just takes a dictionary and then sets the key to be red, the value red. So takes the color and makes it red. Simple so far. Let's say we've got a fruit and say blueberry. If we call the makeRed function on it, then what we'd expect is that it turns into a red berry, hopefully. What happens if we check that color key? Oh no, we had a typo. It didn't have the U in the function, so we accidentally added an extra key and now our dictionary is completely wrong. So what we want is a way of documenting the structure associated with our data set. We want a way of enforcing that structure to make sure that the data set actually has the structure we're expecting it to. What are the names and keys of our data set? What data types do we expect? What constraints do we have on our data? What are some sensible default values? And maybe they're not hard-coded, but just a general guidance for someone using the class or the data set that we're dealing with. And maybe more complex things for more complex data structures like nesting and ordering, optional values. All of these things we've got floating around in our head when we're familiar with a data set, but as soon as we move to collaborating with someone or working on it long term, then we want to be thinking about having a way of documenting this stuff and structuring it in a way that we can reuse. So basically, try and get this out of your head and into the code. If you don't do that, you're going to suffer from mental overload. That's what I suggest. Doing even basic things like refactoring can become risky because have you actually caught everything? Have you thought of all the edge cases? It's dangerous to work with the code if it's not structured in a safer way. So another thing you might be kind of suffering from with the mental overload is the syntax switching, and this is peculiar to dictionaries. And some people might not be bothered by this, but it's worth mentioning. There are different ways to construct a dictionary, so you've got that kind of standard curly brace syntax, but then you've also got this more object-oriented style, which has some advantages. They both have pros and cons. The object-oriented style has a color difference if you're using syntax coloring between the keys and the values, whereas if you're just looking at the curly braces, sometimes just scanning through, it's harder to see what is a key, what is a value. And also, the object-oriented syntax forces you to use strings as the keys, which might be an advantage. But it also suggests that you could do this and access it as an attribute, but you can't do that with dictionaries. So that kind of thing also, I think, adds to the mental overload. So what happens if you want to move away from dictionaries? Well, if you started with dictionaries in the first place to deal with your data set, then you might struggle to grow the code base or change it later. If you are using a dictionary, then it can make it difficult to rename the keys across many files because you don't actually have a centralized place where you keep a record of what the keys are. If you try and do static analysis, again, it's sort of, the string is only defined at runtime, so you're probably not going to be able to use some more advanced tools that would actually help provide some more certainty to that your code is robust. And if you're trying to add methods, object methods associated with your kind of data set, because you're not using a class, you're just using a dictionary, suddenly you don't have a place to put it where everything lives together. So as some of you might have guessed, I'm going to suggest using something like data classes to solve this kind of problem. What that does is provides documented structure to your data set. So in this case, you can see we've got a name for our data set, which is helpful. We're calling it fruit, so we actually know what we're dealing with. We've got a name for each of the different aspects that we're keeping track of. And this is living in one place so that if anyone's dealing with a data set like this in your code base, they know where to go to. You also have the data types and a dot string, which is also really helpful. You can start writing things about the data set that are helpful to know, the ins and outs of how to deal with this. And also in the future, it's very easy to know where to go to add that documentation for other people who are making changes. It's also got that object-oriented style. If you want to access attributes, it's just with the dot syntax, which means you don't have to have those extra characters just for square braces and string quotations, which is quite nice. Also, if you're using an editor, like we saw in some of the earlier talks, you get a whole lot of help from your editor with refactoring. You can do renaming across multiple files. You can get code completion as you're typing things out because the editor actually knows what the structure is, so it can help you. And you can navigate around your code base and do all these more powerful things with the support of your editor rather than just sort of having to keep track of all these things in your head. So what happens if we have something wrong in our data? The data classes provide information about what you should be doing, but how do you know you're actually following your own rules? So in this case, we accidentally put a string where there should be a float. Unfortunately, with the standard data classes library in Python, in the standard library, you won't get data validation. So if you try and construct that class with the string, it won't tell you that something's gone wrong. It will just go ahead and you'll have to wait until you get through to the stage in your computation to realize that something's gone wrong. So how can we do better? Well, probably we should adopt some kind of runtime validation. How can this be useful? Well, if you're dealing with a large data set, you don't have to manually go through every single entry, every single aspect of your data set to find where problems are. You can automatically go through something large and have confidence that you've caught everything. It's especially useful for unseen data sets that are coming in. But also, when you're doing calculations at key milestones in the computational process, you can check that your calculation is actually working as you expect to, and invest some time doing validation to make sure that the structure for your data that you've specified is actually being adhered to. Before you save outputs, before you finish what you're doing, you can check that the final output is correct. And it's also useful for configuration files. Given configuration, have they actually given valid values? You can check that straight away as soon as you load in the file, rather than waiting until maybe something goes wrong down the line. So the way you can do this, one way you can do this is by taking your existing code that uses data classes and use a drop-in replacement from the package called Pydantic. So you can see there the import statements change to from Pydantic.dataclasses. And everything else will work exactly the same way, except now, if you've put in that bad piece of data, then you'll get a validation error raised. And you can see that it tells you value is not a valid float. So now you know that that needs to be changed if you want to have the code continue. What happens if I put in a negative value for weight? Well, that's still a float, so there's no problem, right? Well, of course, negative weight for fruit doesn't make sense. So we can specify additional rules. So you can import the specifier, field specifier to say it needs to be greater than 0. The weight needs to be non-negative. And then this will also raise a validation. So this is really handy. Now we can start specifying a bit more detail, not just about the data types, but also about the additional constraints on our data that we want to be adhered to as we're doing our calculations and for the input data that we receive. So it's worth mentioning, just if you have used Pydantic before and you're familiar with it, you may not have encountered the data classes approach. There is another way of doing it which looks like this. It's basically exactly the same. There are some nuance differences that I'm not going to get into, but basically this uses inheritance, whereas the data classes approach is more for, I guess, if you were dealing with data classes a lot and you prefer that way of doing things. But I haven't talked about possibly a much more common form of data structure, which is tabular data, which I think is actually quite a bit different to the kind of data sets that Pydantic specializes in, which is more kind of key value style nested data structures. And tabular data is actually quite special. There are specific things you do with tabular data structures that you don't do with other data structures. And we have established ecosystems in Python to deal with these, and we don't want to reinvent the wheel, so we want to keep using what we've already got and especially if you've got an existing code base and you want to start adding the structure, we don't want to have to completely change everything to be able to start adding that structure. We want to be able to keep doing our tabular operations like joins and aggregations, and we want to keep using our dedicated data type, which is a data frame. Although there are different data frame libraries, we want to keep being able to use what we've already been using. The issue is data frames actually suffer from many of the same issues I talked about before with dictionaries. The reason for that is we often treat data frames as a dictionary of columns. We use the same get item syntax to access the different attributes or columns of our data set. And as a result, all the same kind of things I talked about before with string names as the keys of a dictionary still apply to data frames with columns. If we look at a very similar function to what we had before, make read, this time it's operating on data frames. Instead of just setting a single key for a dictionary, it's setting an entire column. So if you think about before we had a blueberry, now we've got potentially other fruits as well as rows of our data frame. So we construct that in pandas, and then we have the same bug as before because we don't have a centralized place where we keep track of column names. If I see a function that's type hinted like this, it basically tells me nothing about what the function does. It tells me that it takes in a data frame and it spits out a data frame. What does it do? Does it change the number of rows? Does it add new columns? Does it change columns? I have no idea without actually reading through the function. And perhaps what's worse, I might not even bother doing any kind of functionalization. I might end up just sprawling through a big notebook doing some scrappy analysis, and then it becomes spaghetti code because I couldn't be bothered trying to keep track of what changes I wanted to make in a structured way. I just kind of add columns, delete columns, rename columns as I go through. I start off with some messy columns from the input data set and kind of just run with them until I get frustrated and then get rid of the suffixes or something. It can be really nasty if you don't provide some functionalized structure. And if you don't functionalize it, you're not going to test it, which is another problem. So how do we get that structure? How do we specify our column names, the data types, the constraints on our data, sensible default values? Because column names can be nearly anything. So one solution, and there are many, but I'm a big fan of, is the package called Pandera. And this is perhaps less well known than Pydantic, which is the most popular data validation library in Python. But Pandera actually has a very, very similar API to Pydantic. And as you can see, it looks basically identical to the example we had before, but this time, instead of inheriting from Pydantic's BaseModel, we inherit from DataFrameModel. And DataFrameModel kind of implicitly is telling us that we're dealing with a data frame-like structure with multiple entries per attribute. So color, even though it says string, kind of thinking that's a column of strings. Weight is a column of floats. How do we use this in our code? Well, it's a little bit more complicated, but it's still really quite clean. You have a type hint, which allows you to specify what kind of data frame you're dealing with. In this case, I'm being explicit. The makeRead function takes in a fruit data frame and it returns a fruit data frame. Of course, you could return a different type of data frame and specify exactly the type of structure that we expect. And so you now know exactly what columns are meant to be coming in and what columns are meant to be going out. We have this check types decorate, which tells you exactly what structure is coming in and validates it. So you now know that if you run that function, that it's guaranteed at runtime to be validated that the input and output data frames are being checked. If you don't want to use that decorator, then there is a validate function that you can call at any time from the class. And then the other thing that's maybe a bit unusual about this is the column names are not accessed by attributes. So the fruit df in this case is just a standard pandas data frame at runtime. It's not some kind of special subclass. You are just using the exact same classes that you were using before, but we're using a different syntax for accessing column names. So our column names now live in the class as basically an enum of column names associated with this data frame type. So if I want to access the color column for fruit df, then I retrieve that from the fruit class. So you can see there, fruit.color gives me a string, and fruit.weight gives me the weight string. So I now, if I want to rename the name of that column, I can do it in one place and it will propagate out throughout the whole code base. The thing with column names, and one way why we probably want to do it this way using sort of get item syntax rather than attribute syntax, is because column names for tabular data structures are actually quite important to be able to access in their own right as first-class objects. For example, with merges, we will specify a list of the column names that are used in the merge. It becomes a lot cleaner to be able to specify the names rather than the columns themselves. So, of course, the pandas API expects column names, so you need to be able to access those when you're writing functions. Same thing for aggregation, group by, we want to be able to specify a list of columns that we're aggregating by, and selecting, we want to select the weight column. Again, we can just access this from the class as a string. If we're doing plotting, a lot of plotting libraries, like here's Seaborn as an example, they take in a string as a column that tells you which axes take which field to plot. So you know that on the x-axis where you're going to use name, and on the y-axis we're going to use weight. So all of these different examples just show it's quite common to access column names as objects in their own right. And there's plenty of other examples, but hopefully as you're working through a code base, you'll kind of recognize when you're using a column name and start trying to put it into a class rather than just having it as a raw string. There are quite a lot of other Pandera features, which I'm quite a fan of. One of them is you can write custom checks. Same in Pydantic, but in Pandera you can basically write checks on columns to make sure that the column adheres to some kind of structure. It might not be individual row by row, it could just be across the entire column it needs to sum to 1 or something more complicated like that. Or if you're doing something even more complicated, you can do a check on the entire data frame. So it's sort of building in tests at runtime that you can be executing throughout the process. It's also useful because you can synthesize example data sets. So once you've specified all the data types, Pandera can generate you 5 rows that comply with that exact specification. That can be useful for unit testing. It can also be useful for checking that you have actually thought of all the cases. Like with the fruit example, I might have generated an example data set and realized that some of the weights were coming out as negative, and then I'm thinking, oh no, I need to stop those being negative, they need to be non-negative, right? And the other thing is that Pandera does support alternative data frame libraries like PySpark, GeoPandas, so you can get all the benefits of the existing framework that you're working with without having to refactor everything. And there's plenty of other features, so I encourage you to look into Pandera, especially because it is a slightly less well-known library. But the main takeaway is not these specific libraries, it's about a more general concept that hopefully you're seeing this pattern of a way of structuring these classes when you're dealing with data sets, and I'm going to call them data-centric classes. What do I suggest you use? If you've got these sort of dict-like key value nested structures, data classes, and Pydantic. If you're using a tabular data structure, so something 2D, I recommend you use Pandera. And if you've got something even more complicated, I haven't had time to talk about this in detail, but there's another package called Dockeray, which is really for high dimensional data sets, especially if you're doing something with machine learning. If you've got sort of a 5 by 4 by 2 by 3 array and it needs to be that exact size, you can specify it needs to be that exact size, and then it will check that. And likewise, if you're dealing with more complicated data sets like images or video data sets, then it will just natively handle those as arrays and make sure that everything's following the structure you'd expect. What do you get from using data-centric classes? You get documented, readable code that's easy to navigate and easy to understand. You get safer runtime behavior because you can opt into this validation functionality when you need it. And you also get more streamlined debugging and testing because, again, you can basically lean into this validation functionality and find out exactly what's going wrong. Pandera, for example, allows you to enter into the exception object and inspect exactly which rows of the data frame were non-compliant with your validation. So you can quite easily dig into the exact causes of what's going on. So hopefully that's been a good overview of one way that you can kind of add some more robustness to your code that deals with data sets, especially structured data sets like tabular data structures. But happy to take any questions.
Thank you. I think we've got time for maybe 2 questions, and then we have afternoon tea.
I've been sort of not an expert in the sort of looking at the machine learning stuff and all the examples that you'll see on AWS. Some things, not a single one of them has used something like that. Do you think that's actually, it seems like such a simple concept to document this area, and from your experience, it's just not common in that space?
Yeah, I think people come up with their own solutions, and there are actually so many data frame validation libraries out there. And as you saw, data classes, there's a whole kind of ecosystem that's developed around that. But I think tabular data structures, for some reason, haven't been given the same kind of love. That's why I think it's important to look into the options. But I think Pandera is a good one. I think people are giving more and more attention to this stuff as we're maturing from scrappy data analysis in notebooks to more productionized environments. Yeah.
Thanks for the talk. Just curious, are any of these tools or maybe alternatives, is there possible to run them as part of the static sort of analysis rather than runtime?
Yep. Pydantic is extremely well supported by MyPy. Pandera also has MyPy support. The issue is it's much harder for pandas to kind of play nicely with types for various reasons. So it's harder to know exactly whether a column has preserved its data type. So you kind of have to trust that the type hints that you've provided are actually adhered to, and that's we lean into your runtime validation to get that confidence. But yeah, there is definitely support for static type checking.
Hello. I might be one of the reasons why there's so many different data structure custom-made ones. I think it's very useful to know how to create these by yourself. Do you recommend that we just use these pre-made data structures to get more standardized, or what?
Well, I think it really depends on the domain that you're working with. For example, tabular data structures, I think, for people who are working mostly with those, taking an off-the-shelf solution like Pandera is going to be really useful. And obviously you need to specify all the exact columns that you're working with, but all of that functionality that people are going to use over and over again, it's going to be there. For more bespoke kind of data structures, that's where mixed up. That's where Pydantic and Docker Array come in, because you can have a lot more ability to just specify the complexity of your data structure and add object methods that are bespoke for your application. But I think one of the reasons why there hasn't been as much attention given to these sorts of class design structures is because in the past, Python didn't have a syntax for doing type annotation-based classes that are now supported by data classes and there's other libraries. Before, you had to create a specific dunder init function, and it became quite clumsy. I think that's part of the reason, but I'm not exactly sure.
That's all the time we have. Thank you so much, Nathan.